I'm Tyler Hashimoto.
I'm Jacob Landseedel.
And I'm Nick Smith. This is Lab 5 Spherical Aberration, and we're grouped Wednesday at 6 to 10.
Spherical aberration is caused by replacing your ideal reference wavefront with a new aberrated wavefront. That's the spherical aberration. That is changing the wavefront radius of curvature with a new radius of curvature that you can see the green from the black. Changing your radius of curvature will cause a picture that looks like this, where your wavefront now has a differing power throughout the position on the wavefront. So your marginal rays will come to focus before rays that are in the inside of your spherical wave. And so now you have a marginal focus where the marginal rays focus to, and you also have a praxil focus, the idealized focus for the idealized wave. So now when you come into something like this is the image plane. You now have your reference spot, and maybe this is your new spot from your wavefront. You can calculate your ray errors epsilon x and epsilon y, which are your errors in the x and y axes respectively, by these formulas here. So how we look at spherical aberration is we have a ray fan, and this is at marginal focus with spherical aberration induced, and this is showing that the two marginal rays and your on-axis rays are intersecting the optical axis, leading to a deviation of 0. However, the rest of your pupil has a cubic distribution as you move from the optical axis.
The spherical aberration dominated ray fans are governed by these equations right here for, as you can see, epsilon y and epsilon x have basically the same shape because, actually exactly the same shape, because they just use 8 f number times WO40 and negative 8 f number times WO40 as the max and mins. Right here we have our equation for spherical aberration, WO40. Right here is the semi-diameter of the lens, the power of the lens, and 0 is the index of refraction of the medium surrounding the lens, which is air in this lab. N is the median, or the index of refraction of the lens. B is the shape factor, and C is the conjugate variable, which is defined as U1 plus U2 prime over U1 minus U2 prime, where those are the two angles. As you can see here, C equals -1 when U1 is 0, because it's just -1, and then likewise when U2 prime is 0, then C equals +1. And what we want to do is we want to make B equal to this in order to make this equal to 0, or as close as we can get. And so to do that, we just make the shape factor be different by changing the shape of the lens, or in the case where we did in the lab, we just simply rotate it. So if the light's coming towards the plano side, shape factor is -1. If it's coming toward the convex side, shape factor equals +1. The setup of our system is so that the laser goes and reflects off the pentaprism 90 degrees, goes through one of the 11 holes in the Hartmann mask, goes through the lens and through the microscope and onto the screen back there. As you see here, the laser is going through the far right hole of the Hartmann mask. This corresponds to the marginal rays on this diagram, which, as you see, converge before the other rays because they're at the steepest angle. Now we know we're at the marginal focus because we scooted up the microphone as close as we could to the lens while still getting a perfect image. Ideally, the far right and far left beams would both focus at the same point. However, the system is slightly asymmetrical, so the right beam focuses before the left beam, therefore we're using the right beam.
In this section, we're at the marginal focus, so we're going to start at the left-hand side of the Hartmann plate and move our laser to each hole as we go through. And so as we go through each of the Hartmann holes here, we're going to measure the deviation measured from our central spot with the pen mark here to the beam center.
This graph shows the data we recorded of the spherical aberration at the marginal focus. We see what we expected with the marginal rays and the center being very close to the optical axis, showing very little deviation. For this experiment, we're measuring the deviation of the beam off of the aligned reticle, and we'll be, instead of using calipers to measure it, we'll be adjusting the micrometers here to bring it back, overlaying the reticles. This graph shows the data we recorded from the X-translation shift of the micrometers at the marginal focus, and we see the two marginal rays and the central ray are very close to the optical axis as we expected.
In this section, in order to reduce spherical aberration, we reflipped the lens around and repeated the steps that we did in the measurements in step D. After we got our measurements, we produced our graph here that shows that we've reduced spherical aberration and that all we have left is really just defocus.